Right, so our last problem on this exam, there's this ball pitching machine where a ball comes up a little chute and goes through this circular tubey thing with a radius of r. When the ball leaves the device at a height h above the ground, it has launch speed v0, and it travels through the air and lands a distance d from where it was launched. So the ball's trajectory is going to look like that or something. So this says, if the ball lands a distance d from where it was launched, find an expression for the initial launch speed v0 when the ball emerges horizontally from the machine. So this is saying, given that it lands at distance d and it started out at a height h, how do you express v0 in terms of those two things? So this is a kinematics problem because we're not really interested in what's happening with this thing. We're asking, if you know where it landed and you know how high it started, what was the launch speed? So while it's flying through the air, the only force acting on it is the force of gravity, which is a constant force. So that means you're going to have a constant acceleration only in the y direction. So if we look at our expressions for kinematics, which I know kinematics are everybody's favorite. So here's the kinematic equation. So these apply in every direction. So we have an x direction here and a y direction here. So we were given the height h and the range d. Both of those are positions. So I'm going to start with the position equation for both the x direction and the y direction and see where that gets me. I think that's going to be all we need. So let's do the x direction over here and the y direction over here. So our equation in the x direction is x of t is x0 plus v0 x times t plus 1/2 ax t squared. And in the y direction, same thing with y. So v0 y times t plus 1/2 ay t squared. Okay, so this is our initial point, and this is our final point. And let's put our origin right here. Okay, so start with the x direction. So what's our final x position? The final x position is d. What's our initial x position? That's where our origin is, that will be 0. And what's our initial velocity in the x direction? Since this is totally horizontal, v0 is our initial velocity in x. We don't know what t is. And there's no acceleration in the x direction because the only force acting is gravity and that x straight down. So this is 0. So our equation in the x direction is just d equals v0 times t, which makes sense. This says we have constant speed in the x direction. So we multiply that speed by the time it's in the air. That'll give us the displacement in x. In y, our final y position is 0. Our initial y position is h. Initially, the velocity is horizontal, so the initial y is 0. And then we do have acceleration in the y direction. Our acceleration in the y direction is negative g, negative t squared. So this gives us 2h over g equals t squared, which means that t is the square root of 2h over g. Okay, so I have two equations. And I want this, but I don't know t, but I know everything else. So if I just take this and substitute it in for t over here, I'll get my answer. So v0 is d over t. And now substituting that in, that's d times 1 over t, so that's the inverse of this, which is g over 2h. And that is our expression for our initial speed, v naught. Okay. So now we want to find an expression for the magnitude of the normal force, Fn, exerted by the curved part of the machine on the ball just before it's launched horizontally from the tube. So we want to know, just before it's launched here, what's the normal force on that ball? So let's draw a free body diagram. So the picture looks something like this. The thing comes up and it curves around, and we want to know what's the normal force there. So at this point, we need to figure out what forces are acting on it to draw a free body diagram. So gravity is pulling it down, and it's also touching this piece of metal. So there's going to be a normal force that's also exerted straight down. So to figure out what that is, we better sum the forces. And in this case, that's in the y. They're all in the y direction. There's nothing in x. And that's going to be equal to the mass of the ball times the acceleration of the ball in the y direction. So let's say that this is the positive y direction. So this will be the normal force plus the force of gravity is m times ay. Now, how is this ball accelerating? Well, since it's going around a circular track, it's moving in a circle. And if something is moving in a circle, that is for F equals ma, that's our specific case 3 for circular motion. If an object is moving in a circle, it has a radial acceleration, an acceleration that points inward, that's equal to the speed squared divided by the radius, which this acceleration comes just from the fact that the acceleration vector is changing direction. So our ay is v squared over r, and our velocity at that point we found was v naught. I'll put a little naught there. And we're after the normal force n. So n is m v naught squared over r minus the force of gravity, which is the mass times g. And then we figured out what v naught was in part A. We said it was this. So if we plug that in here, we'll get n is m over r d squared g over 2h minus mg. And you could clean this up a little bit if you wanted to. You could pull out mg. So mg times d squared over 2rh minus 1. Okay, and then last but not least, find an expression for the minimum launch speed so that the ball will emerge horizontally from the pitching machine. So what's going to happen is if the ball is not launched with enough speed, the ball is going to come up and it's going to flump off, it's a technical term, before it gets to the end here. Just like, it's like a roller coaster car that isn't making it around a loop-de-loop. So if we want the minimum speed for it to leave horizontally, we want to know what's the minimum speed where it will still just barely have a normal force when it leaves. So the limit there is setting the normal force equal to 0, because that's the point at which we know it's going to lose contact with the track. So in this case, we're really starting with the same thing we started with in part B. We had the sum of the net force is MAY, and that force is the normal force plus G is mv naught squared over r. So we're looking for the minimum speed. So this is really, we want the minimum one where this just barely goes to 0. So if we take this to 0, we'll have FG equals mv min squared over r. And FG is mg, so mg is mv min squared over r. The masses cancel, and solving for v min gives us the square root of g times r. And that is practice exam A.